Welcome back to the LevityZone. I'm sitting here in Islamabad, Pakistan, amongst the gray South Asian crows and all the life that is happening here in F6 sector. So it's a wonderful occasion to bring this to you. I'm on a work mission here and a science mission. So work is for my wonderful company Elixir Technologies, who I work for now for 30 years, developing some of the original software, which is still used all over the world. And meeting our team, 200 souls here in Islamabad in the laboratory, talking at local universities about information technology and the user experience. And yesterday I talked at a major university here, the original science university called Quaid-e-Azam University in Islamabad, and I'm going to bring you that talk today in the LevityZone. That talk is perhaps the first talk on the origin of life and the search for life in the universe that has ever been offered here in Pakistan. My host is Professor Pervez Hoodbhoy, who's a world-renowned physicist and activist fighting for science and reason in a world, especially this world, sadly, that is increasingly falling under the controlling dark shadows of ignorance and fear. So with that, I'm going to give you this wonderful, frolicky, romping, funny and at times inspired at times, complex at times talk on the new thinking of the origin of life that's all come up in the last couple of years, but with some new additions for the last 3 weeks of travel. And you'll hear about that next. Then following my time in Islamabad, I'm going on this rest of this round the world tour, which actually started when I was at the SAND conference, the Science and Non-Duality Conference in San Jose. And then I went down to Ecuador, to Quito, Ecuador, to review and examine a university that is possibly one of the sites we're considering to host our International Society of Origin of Life meeting in 2020. And my host there kindly took me to the Galapagos Islands, where a lifetime dream came true for me, where I stood at the bay where Charles Darwin came ashore from the Beagle in 1835. And I stood or crouched face to face with 150-year-old giant tortoises. From there, I went to Honeybee Robotics back in Pasadena to meet with and do a presentation for the roboticists who build the instruments for drilling and coring and various things for the Mars rovers, to talk to them about a design of a chisel to fly to Mars on an upcoming or maybe distant mission to break rocks and look for evidence for stromatolites on Mars. And then I flew here to Pakistan. From here, I'll go on to China this evening, actually, to meet with the insurance industry, a burgeoning cell phone, mobile phone, smartphone-based insurance effort that we've enabled in China. Very, very exciting. Make a presentation for them. And then go to Hong Kong and meet more people there, including a world-renowned AI specialist who's designed AI robotics, very human-looking AI robotics, and talk to him about how this origin of life model, which is kind of like an eye of creation, it's a creation mechanism, might be used to create new AIs in the future capable of open-ended evolution and adaptation. So without further ado, I want to take you now from the beautiful back garden of Basit Hamid, his house here in F6. He's our founder of Elixir and my dear friend and mentor and boss for 30 years now. I'll be taking you back yesterday to the university just on the other side of the diplomatic enclave here in Islamabad with Professor Hoodbhoy introducing this talk on a lot of science, and I hope you enjoy it.
It's not an easy task to introduce Bruce Taber because he's got so many diverse interests. He's been involved in designing spacecraft to do very unusual things. He's worked with NASA on that. He's also spent a lot of his time worrying about the origins of life, how life came to be on Earth, its chemical beginnings. He has very recently been in the news, a grand issue of Scientific American, which is principally the work of Bruce and his co-authors. And so it's a matter of great privilege that we have him over here today in the physics department. I will not take up much of your time and simply ask Bruce to begin. But after this, we're going to have a short discussion upstairs in the seminar room. And unfortunately, there's space only for 20 people over there. But those of you who feel really exercised, please do make your intentions known to us. Bruce has got so many interests, so many diverse ones. He's also a person, very interesting person in how he thinks about the world, but we leave that for later. Thank you, Bruce, for being here, and go ahead and start.
Thank you, Dr. Goodboy, for having me here in your home institution, which I know is 50 years old this year, so congratulations. I'm 55 years old this year. But I want to present to you first, the field of the origin of life is actually a very grounded field, but it has been grounded in chemistry until now. Not too much in physics, unless you count classical physical processes, but it's been one of the great scientific mysteries for thousands of years, actually. It goes back into Greek philosophy. There's always the question of where did we come from? And our field is young, perhaps only 125 years old, maybe 100 years old. But it's also grounded in evidence on our own planet. And what I brought here, I'm going to hold up, is a fossil of, basically, this is your oldest, as far as science is concerned, your oldest ancestor. This is a stromatolite from northwestern Australia. And if you can kind of see a little bit, there's these ridges. It's a rock with texture, with fabric in it. It's like a rock made of cloth in a way. But it was spun by individual organisms cementing sand grains together, if you can understand that. So if you're by a lake shore today, you often see a little bit of scum on the edge of the lake shore. That's sometimes called a biofilm. If you don't brush your teeth develop plaque, which is another kind of a biofilm. Biofilms dominate the biosphere. They're 90% of the biosphere by weight in terms of their carbon. They're a massive component of the biosphere. And in a sense, complex life like us is a rare example of microbial communities bumping up and giving us complex life for a short period of time, probably no more than 1% of the time of life on Earth, and then complex life will go away because the conditions for complex life are extremely narrow and rare. We're dealing with this now because I'm on the site selection for the next Mars rover landing site. And Mars is a planet that went out of habitability. It basically died early in its history. And for us to try to find evidence of microbial life on Mars is going to be a big challenge because life ran out of steam in that instance. More on that later. But let's get on a little bit to the subject. So our field was really created by Charles Darwin in 1871 in a letter to his friend Hooker, who was a great correspondent with Darwin. And he had this very famous expression in one paragraph, and what if, a big if we could conceive of a warm little pond somewhere with all sorts of ammonia and phosphoric salts, heat, light, electricity, etc. And this is what everyone knows. They know the warm little pond. But what they don't remember is this expression here, which is important for chemists, such that a protein compound was chemically formed, ready to undergo still more complex changes. He nailed it. This is the actual fundamental problem in the origin of life. How do you grow a compound and keep it from breaking down basically either repairing it, which is what biology does, or growing new ones all the time. And that's going away from equilibrium. Basically, the water molecules are always trying to break your compounds down. Your body is an example of a machine that fights against that entropy, that is trying to break it down all the time. That's effectively what life is. So if we go on the next 100 years, we had Oparin and Haldane identifying that we needed soups. We needed concentrated material, concentrated enough for chemistry to happen. So that's where your primordial soup came in. Then in 1953, Harold Urey and Stanley Miller did an experiment in Cambridge where they sparked a chamber with a compound of gases that sort of simulated, in their minds, the early Earth's atmosphere. And they were simulating lightning going through the chamber, and they made amino acids, which are one of the building blocks of life, by sparking the chamber. This was very famous. This was world news at the time, as famous as the discovery of the structure of DNA, which was also in Cambridge. There was a lot of things going on in Cambridge. 1977 was the discovery of these deep sea hydrothermal vents, think springs coming out of the bottom of the ocean, pushing a lot of material. They were called black smokers at the time. And it was suggested in 1982 that perhaps life could start deep in the oceans. We don't think that's viable anymore because there's always water present which would break your compounds down. That's the short answer. But our field basically investigated that for 30 years without it being able to make a single polymer. When I came into the field 6 or 7 years ago, they were looking for an alternative, and I worked with David Deemer at UC Santa Cruz, and we proposed the alternative, which is back in Darwin's pools on land. To take you on a personal journey of where I picked up this, I want to show you some pictures of where we found it and how we got there. So this was a astrobiology field trip in 2015, up from Perth, Australia, up to this area called Shark Bay, which is a very saline estuary. And it's salty enough that it prevents fishes from eating everything in their path. Therefore, you get these things, stromatolites, which are the great offspring of these. So this is biofilms that set rock together and make basically rock structures. These, they're shown underwater, are stromatolites. They look like stones, but they're made by biology. They're almost like your teeth if they grew with each layer of biofilm. So this is what stromatolites look like. And they used to basically ring all the continents before the rise of complex life. There I am standing with the stromatolites. And if you touch them with your finger and push into them, they're very spongy because there's millions and millions of microbes in there. So the top layer is making food from sunlight. The next layer is doing chemical synthesis, etc. Stromatolites. So we continued for 2,000 kilometers up to this very special region called the Pilbara. And what you're seeing there is the North Pole Dome. And if you look, see this outline here, this is now understood to be the volcanic caldera. And this is a very special volcanic caldera. It's 3.48 billion years old. And it was preserved under lava, 2 kilometers of lava, that capped this area. Because very little of the old Earth is left, the Earth from what was known as the Archean period. There's only a few little pieces of that Earth left because continents are in constant movement. They're being subducted down, they're being broken up, they're being kind of consumed. And this piece of Northwest Australia is the largest intact piece of the old Earth's continental crust that exists. So if we go here, there's our bus. This is in the middle of the North Pole Dome. That's sort of the geologist's point of view of it. And there's more stromatolites. They're everywhere. This is a great big slab of stromatolite, indicating, in this case, a marine shoreline, an ocean shoreline is there. This is looking from the top at the domes of the stromatolites. These are about 3 billion years old. Here's one that's cut in cross-section. And here's one that I took, which shows black chert. And then these little ripples there are also these biologically created structures. And in the black chert, if I took a thin section of that chert, I might find a microfossil. So that's the other type of biological evidence. They're very rare, but they're preserved in black chert. So there's the two kinds of preservation. You have morphological preservation that's just the structure laid down by the biology, and then you have rare microfossils in this strata. There's Martin van Kranendonk, who's the main geologist of this region, and there's me looking just at stromatolite on the surface. And that's what you see just everywhere. It's so well preserved there. There I am with stromatolites at the Strelly Pool locality, which is their discovery outcrop from about 50 years ago. There was a very, very exciting discovery 3 years ago, and this was published in Nature Communications in April. It took that long for the peer review process. This is geyserite. So a young student who's your age was working with Martin van Kranendonk, and she noticed this little area, this little white band in the rock, and she said, we've got to go back there. So they went back there, they took a sample of it, and it turns out it's what's known as geyserite. This is geyserite. And see those black and light bands, that's the same as minerals today. They're made by when a geyser comes up and splatters down on the rock. It deposits things. This rock could only be made by a geyser. So it had to be a freshwater environment on land. It's not marine. So then that caused Professor van Kranendonk to rethink the Pilbara as a volcanic caldera, not under the ocean at all, which is what most evidence of that age is at ocean shores, but in fact was a hot spring. So then they started comparing everything else, and they found these. This is what microbes leave in the rock. These are called terracets. And this is silica gel with microbial matter in it. And here's the terracets from 3.5 billion years ago, in very rare find in the Pilbara. Then they found something even more remarkable. These little spherical contusions, which they are interpreting as trapped air bubbles, trapped oxygen bubbles in the silica that preserved the stromatolites. There's evidence for trapped air bubbles. This would indicate metabolism, metabolic activity. It's the oldest signs of metabolism on the Earth at 3.5 billion years ago. And those bubbles tend to be trapped in the sort of gooey, slimy material that microbes make for themselves to glue their communities together. So this is remarkable in its own right. This is why this is also world news, and it was the basis behind this Scientific American article in August, was this hot spring discovery. And then what we did is place our origin of life model into the article, because we're collaborating with this team. So the rocks tell you a story, and they tell you the story in reverse. So here we have the geyserite at 3.5 billion years ago. This is a sample I picked up in another locality, which was basically hot subsurface vein stromatolites at about the same age. Here's a lakeshore stromatolite from 2.7 billion years ago nearby, indicating there was a lake there. And this is the modern stromatolites, all the way back to the present day. So the rock record is really important in the question of the origin of life. And it's mostly been not part of the origin of life community. And what Dave and I are doing is bringing the geologists into the community, because all breakthroughs in science are done with interdisciplinary collaborations. So here's how we think that life can start in Darwin's warm little pool, except we modify his claim or his insight and say that it was probably not a warm little pool, it was a hot little cycling pool connected to hot springs. And you'll see why in a minute. But here's our landscape. So what happens on a landscape? You get rainfall, you get dust particles coming from the solar system. That can accumulate in rock pools, and the rocks themselves can generate important nutrients for the start of life. So it's a concentrating environment. If this material fell in the ocean, it would just simply dilute. And this is why chemists never liked an ocean origin, because they're in a dilute solution pretty much all the time. So the land can collect, concentrate, then cycle through hot springs, generate an early form of life that then can distribute across the landscape and be subject to selection pressures, almost like a computational selection. And then the ocean shore is the extreme world, the extreme environment, because you have salts and a lot of things that are very tough on biology, actually. So let's go on. So this is our work in the field. This is Dave, my colleague at UC Santa Cruz, adding material to a hot spring pool in Kamchatka, Russia. What he did is add the material and it immediately formed membranes. So this is material derived from asteroid impacts or meteorite impact material, formed membranes in this little warm pond immediately. And membranes are the number one thing that you have to be able to create for life to begin. This material derived from the study of this meteorite, which fell on Australia in the 1960s, and it's called the Murchison meteorite. It's very famous. And if you grind up a powder of this and put it into solution, you form membranes, and it has over 70 amino acids. So the building blocks of life can come from space. We don't need to spark chambers to do it. Thank you very much, Miller and Yuri, but we don't need that. We have plenty of material from solar system infall. So that's the feedstock. So what Dave also discovered, which is the basis of our work, is that if you have little dishes of compounds that contain mixtures of the building blocks of RNA, which is AMP and UMP is what we use, and you put that mixture into a little dish, which is in this rotating system, this is from our laboratory, and you hydrate it, and the dishes come around and they go through a dehydration station, and you keep doing this, you can grow RNA and make it longer and longer and longer. And the way it works is that between these layers of lipid, the membranes that you put in, which could be fatty acid membranes or could be modern phospholipid membranes, these are called amphiphilic compounds. They form these beautiful membranous structures. When the membranous structures dry down, they compress the building blocks of living systems between the layers. And then those, as water leaves, they stitch together like a zipper. And you can create huge numbers of random sequences. Up to 150 base units long, we can grow these polymers. They're random, though. Life is able to write its own code, but the code is random. So let's go on. We use what we call nanopore sequencing to determine that this was actually RNA, and we use ordinary gel technologies. And our colleagues have done peptides, which is amino acid building blocks. So here's me trying to do this in the field at a hydrothermal volcanic field in California last year. And there's my slide tray in a vent gas environment. This is quite a dangerous place because people have lost their lives in this location. And we were able to polymerize RNA using the moisture in the vent gases alone on mineral chips. So we try it in the natural world. Here's another place that we just visited. This is in Yellowstone National Park in the United States, and it's an amazing place. It has thousands of these pools everywhere, different geysers. The most famous is Old Faithful that goes off about every hour, and all the tourists gather, and then it goes off, and then they come back, and that's what Old Faithful is. This is a special pool that has highly alkaline waters, and what it actually creates is these little gels. This is little gels that grow into a mineral called sinter. And within the sinter, within the mineral, is a ton of biology, lots and lots of biofilms. So biofilms are growing in these environments. And what I did was I introduced some of these waters to solution, and right inside this vesicle with my little lipid solutions, I can introduce this alkaline water from the natural world and shake it up, and I made trillions of little compartments called protocells. So that works in the field. You put it all together, if you can make compartments in chemistry, and you can make polymers in chemistry, and you can get the polymers into the compartments, you can potentially start life. So here's what we did in the lab. Through several cycles, these glowing little bubbles here are the compartments containing RNA that was made randomly. So we verified this empirically. So we used decanoic acid, and these are what we used. So bring it to another analogy. How many of you are computer users? Is everybody a computer user? How many of you are deep nerd users of computers? Nerds. How many of you are in computer science or computer engineering as a field here at the university? Computer science? Great. There's a few deep nerds here. So here's the example. So you've just seen a bunch of chemistry in a different language, a scientific language of chemistry. Let's give you in an almost everyday language of computing, because everyone's a computer user now. So what if you had a computer that was programmed by punched paper tapes? Dr. Hoodboy will remember these days, these terrible days, that computers were programmed by either punched paper tapes or cards that had little square holes in them, and you fed them in, and they hopefully worked or didn't work. But that was the programming medium for early personal computers. But what if our punched paper tape did random programs, to just punch things at random? Let's make a system that has a reader for these tapes, and it puts it into a primitive computer. This is a model of an Altair computer from the Homebrew Computer Club, because I have a large personal computer collection. And the computer is powered by energy, and it cycles. It pulls in these tapes, and it tries to run them, and it's running them in its little processor, and they either crash and go into the crash trash, or they run. So if the program runs, the simple decision is made, say program A ran, let's punch a bit more tape, stick it on with program A and make program AB or program AC and try to run that. And if that runs, you evolve your computer. So now more functions can boot up and you get a computer with a keyboard and a screen. And you keep evolving it, you get a laptop, you keep evolving it, and you get a smartphone. So this is evolution of software and hardware together. This is a very inefficient way of evolving hardware and software. So we hire people called engineers to do this for us, only slightly better probably than random program writing. But this will actually work. You can actually write software systems that do this, that use random programs through selection to gradually get more and more functions. So where do we find this in nature? So here's our whole crazy system. We find it in nature in the little pools. The random tape puncher is our polymerizer, making those long chain polymers built from the building blocks from space and from the geology of the Earth. The polymers are programs. They're random programs. The computer that they're going into is a warm little cycling pond. The programs that the polymers are running in, the system is protocells. They're basically little polymers inside bubbles. And they either pop or they do not. So here's our Charles Darwin overseeing this process. And he's saying, well, that one popped and it lost all its contents, but that one survived. And the ones that survive can come down when the pool dries down and come down and they're your population. We'll see what happens to these populations. So here we have a cycle. We call it our coupled phases cycle. That was our paper of 2 years ago. So you have a three-way system. That one is drying down to make your films and make your random polymers. The wetting phase puts those polymers into these bubbles. The testing phase, they either pop or they do not. And then when the bubbles, the survivors, collect down at the bottom of the pool, you have a chance for interaction. So it's a three-way system. Now, when you look out into the countryside, you see the system still working. So you have a very dry season, right? And suddenly the rains come, like they've just come here. Suddenly the soils are now moist, and plants start growing. There's a lot of metabolism, constant metabolism, once the rains have come. And they're doing a furious amount of metabolism because it's going to dry out again. So what do they do as they're doing it? They grow these things called seeds. And the seeds are capsules to preserve the polymer called DNA and RNA and others, such that they can get through the next dry cycle. And then when the winds come and blow the seeds around, it distributes them into environments where when they become moist again, they go through the cycle. So basically the pattern of the origin of life may be found in the world today, or the other way around in a sense. So we've proved this empirically with drying down our lipids. This works. Encapsulating the polymers in the protocells. And then we see in the bottom of our dishes the survivors that have come back. So this is a cycle that's now been proven in science. And then what happens when the survivors come to the bottom of the dish, they fuse together. They join together because when they dry down, the membranous compartments go boop, 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 and fuse back into layers. So it's a complete closed-end cycle. And this is called a kinetic trap by chemists. So we found the kinetic trap, but there's also another term for it, the progenode. a term coined by the great evolutionary biologist Carl Woese and his graduate student George Fox in the 1970s when they discovered the third branch of life. They named the progenote as the boot-up phase of the living world, and we'll see how that might work later. So let's take a look at how the whole thing goes together. So this is the artwork that I came up with about 2 years ago, and we've been rendering it like crazy. Scientific American did a version of it, which I can show you here. This is, in science, you rarely have the opportunities of in your lifetime of creating an image that goes out to the public, that becomes the image that not only the public uses to understand a new theory or hypothesis, but our colleagues can also use the same. So we worked on this for 2 years to get it right. And then Scientific American did this beautiful treatment, and you can see the thing, that the circle there that has a spiral in it. The brown part is drying, the blue part is wetting, and this little thing that's opening up here is the actual collection of protocells, the gel we call it, the third phase, the moist phase. Call it your bathtub soap at the bottom of your bathtub that's accumulated when you drain your bathtub. So they actually did this beautiful job to explain it for the public. Here, you can see hung there in the poster is the full poster presentation that we used at our last meeting. But let's take a look at it on the screen. So what we have is step one. We divided this into 7 steps. Synthesis. In the early solar system, as the planets are forming, as the dust is accumulating, as ices are melting, when the star turns on, when the sun turns on, you get all this chemistry that's happening. And you have the chemistry that occurred between the stars, called cosmochemistry, that made large amounts of organic compounds, were made in space. They accumulate in this dusty disk around the star. And we can see this in exoplanet research. We can actually see these disks now. We can see shadows cast across these disks. But our solar system wouldn't have been any different. And so it had a lot of material, and this material is falling down onto the landscape, and it's accumulating in our aqueous environment, so in these ponds here, which gives us our organic chemistry. So the building blocks we get by grinding up meteorites from this period, from the age of the Earth, we get the chemistry working in the lab. So it's plausible to happen on the early Earth. You get concentration, enough concentration in these pools, and you get the formation of structures, lipid layers, membranes, more complex chemical structures. And then if this material finds its way into a sort of an ideal pool that's being driven by a geyser, where it's filling and being drained, or filling and drying, and filling and drying, you could get this engine starting, the cycling engine, the 3-phase engine. It could start to lift the functions of biology, the very most primitive functions of biology, into existence, such that you generate basically a mass of protocells that's tough enough and is doing enough metabolism, and it's sort of more self-sustaining, that when this washes out of this pool into other pools, it can actually grow again. So think of like your bathtub soap. What if you could take the soap from the bottom of your bathtub, but it got in a little intelligent, right, through lots of bath sessions, and you could put it in your sink, and the soap bubbles would multiply, and there would be more of them. This is what we want to get to. This is now the speculative part of our theory, that this gel, that this collection of little compartments can evolve molecularly, and then it can be distributed to other pools, and then develop the functions of the living world. And some of those functions are shown here, where if these progenotes flow into a stream, they have one problem. There isn't enough food to eat. Because these are dilute freshwater environments, usually neutral pH. If they hit a lake shore, it's even worse, because it's even more dilute. So by the time early life or progenote forms end up in these environments, they have to be capturing sunlight to continue. So it's sort of true by definition. If you're in a dilute environment, you're not making food, you're not around. So until the next set of progenotes arrives that can capture sunlight to make some of the building blocks you need, they're just going to be trapped in the chemical feeding pools. So once that happens, they become more robust. And this is pretty much what happens in the living world today. Every time an organism is placed in a new environment that stresses it, it evolves. So it's the same pattern. So you end up, for instance, in this estuary next to the ocean. And the oceans were coffee-colored back then. They were full of dissolved iron and many other things. You had no oxygen in the atmosphere. You had acid rain. You had lots of asteroid impacts all the time. It was quite a different planet. Orange sky, probably. But here they've got salts coming in from the ocean, which are bad for membranes. If you eat a lot of crisps, right, salty crisps, or maybe a dal that has too much salt in it, what happens to you? You need to drink a lot of water, right? Sometimes your heart rate goes up. That's because your cells are stressed by the salt. And each cell is trying to get the salt out. Get it out, get it out, get it out, because it's not good for it. You sort of feel bloated. You feel like, too much salt. And life has to deal with salt by pumping it out. And so this is why the oceans are not the place where life can start, because it's a stressed environment. And then the last stage is the colonization of the entire planet, is when you get these stromatolites. They're robust, they can survive tides, storms, salt, etc., and they grow their rock towers that you just saw, and they can colonize the planet. So here's the rock record. There's the geyserite from the earliest phases of life. The lake shore, here's some lake shore that would be made in this environment. And here's the seashore, a seashore stromatolite made in this environment. So this is the fossil basis. This is our article, which I just showed you, and this is how they interpreted it for the issue. So now the whole world knows about this whole hypothesis. The good news is this is testable. In science, we've never had a testable hypothesis for the origin of life. And this is testable at many levels. There's many experimental protocols that can be done in each step. So now, how many of you are from astronomy clubs or interested in astronomy? We've got astronomers here. So this new information has huge implications for the search for life in the solar system, and maybe the detection through spectra of a planet, an Earth-like planet that might support life in much farther from the solar system. So this is the mission that I'm working on. It's called Mars 2020, and it's a big rover. It's about the size of a Pakistani Suzuki car. Maybe a little bigger, actually. Suzukis are really small. It's amazing you can get like 6 people in them. I have no idea. It's the miracle of Pakistan. It's not water for gasoline. It's how many people can get into these cars.
Actually,
7? You can get 7 in those? Wow. So this is our Suzuki. A little more expensive, a little more costly. But its mission is launching in 3 years. Its mission is to look for evidence for life on Mars. So it's not strictly a geochemist. It's not strictly a geologist. It's actually a geobiologist for the first time. And the argument that I'm making with NASA, with our team at Arizona State and the Australian colleagues, is you've got to go back to where there was a discovered hot spring on Mars. They found an evidence of a hot spring. This is my rock hammer next to stromatolites in Australia, which is what we need to be able to do, is break rocks on this mission. This is the famous hot spring discovery by Tara Jokic, the student who's your age, who saw this band. She saw this band, and it was almost nighttime. And it was speaking to her, almost like in a mystical sense. She just couldn't get out of her mind. And they were going back to their vehicle, and it was so dark they got lost, her and her colleague. And she just remembered this. She said, we have to go back here because there's something about this that's different. And it turns out that is the geyserite. That's the hot spring, the proof of the hot spring on Mars. And that's a piece of it that I brought back last year. Now, jumping forward to Mars, this is a meeting I attended in January 2003 to pick the landing spot for the first 2 rovers. And this is the actual hand count of people voting to send the Spirit rover to the Gusev crater. And I was just an invited guest at the meeting. I couldn't vote, so I didn't bother putting my hand up. So instead I took a picture because I thought this would be historic someday. And it actually turned out to be. This is the meeting in 2017 to pick the landing site for Mars 2020, for the big rover. And there's our very nervous team there. very nervous because there's now 300 people in the room instead of 25. And there's many careers at stake. And so we're presenting to 300 geologists mostly. We're presenting a case for where life may start on Mars. So this is a lot of words here, but basically if you think that that life has to start in a hot spring, that actually tells you where to go on Mars. You have to look for where the chemistry might have worked 4 billion years ago. If you don't go there, you're just going to find a bunch of rocks that are tremendously degraded and changed by climate. So if terrestrial hot springs are a driver for life on Earth, they also preserve evidence for life really well, as we saw from this guy. They're able to preserve evidence. So it just makes sense to go to where life could be established and look for it. Now here's the key thing. The hot spring on Mars is a place where life can start. They're a likely place to search for the last and best preserved accessible evidence for life. So if life was starting on Mars in a hot spring setting, but Mars was drying out, it didn't have a magnetic core, was losing its atmosphere, and by 1 billion years in, the oceans had just dried up. And the atmosphere became very, very thin, and you had high ultraviolet radiation at the surface. And you had what are called perchlorates, which mean you can't grow potatoes on Mars. So, you know, the Martian movie is wrong, sorry, and you can't grow potatoes there. So it's a planet that was dying, was actively dying. So if you had a start for life, if it started in a hot spring, it would have to go underground for the protection of the rocks. Hot rocks, it's called the refugia. That's what the biologists term this. And it would have had the best access underground to the plumbing of hot springs, going down through those hot water channels, and it would have been there, and that's where you'll find it. And unfortunately, we don't have the technology to drill that deep. And the chance of finding microbial life is really small on Mars. But we do have the chance of finding something like this on the surface. And that's what the argument I'm making. We need to be able to break rocks on the surface to find evidence. So here's the place we want the NASA team to send the rover. This is the landing ellipse for Columbia Hills. And Columbia Hills was already visited. These are real pictures of Columbia Hills. This is the Spirit rover in 2005, 2006, driving over this ridge, and they saw this. And they said, what is that? That's different than, you know, I can't hardly read these landscapes, but the geologists would look at that and say, there's something about that. And they drove down to it, and this is the rover that did the driving. It's called Spirit. It's solar powered. And they drove down to it, and this is what they found. This interesting rock outcrop that had volcanism, it had fluvial activity, it was a lake shore, but it had lots of diversity of silica and carbonates, and it was probably about 3.7 billion years old. And then they were wondering